Fundamentally, a resistor in a circuit is a device that opposes or resists current flow. And the equation that we use to keep track how effectively a resistor resists the flow of current across it is Ohm's law. And so you can see here, whether we choose to write the voltage drop across the resistor as delta V or just write it as V, those symbols are being used identically. So the V in this case is telling us what the voltage drop is across the resistor. That's equal to I is the current flowing through the resistor and R is the resistor's resistance. And so this is the fundamental relation for resistors, and it really tells us how much voltage does it take to drive a given current through a circuit. Now we can rewrite Ohm's law to solve it for R, and notice that what it tells us is that the resistance, the value of the resistance of the resistor, is the ratio of the voltage across the resistor to the current flowing through the resistor. And so what this means is if you think about two resistors, the one that has the larger resistance value, well, either it has to have a larger voltage drop across it for the same current, or if your two resistors have the same voltage drop, the resistor with the largest resistance will have less current flowing through it. You can talk about resistors being either ohmic or non-ohmic, and those phrases are simply telling you, does R remain constant or not? So when you think about V equals IR as an equation that we can graph, we put V on the vertical axis, you put I on the horizontal axis, and then Ohm's law says, well, R then is just the slope of the graph at that value. And for ohmic materials, that slope basically remains constant as you change the voltage across the resistor and therefore change the current through it. For non-ohmic materials, that slope changes. And so the graph of V versus I for a non-ohmic material, instead of being a single slope that's constant, that slope simply changes as you vary either the current or the voltage. The units of resistance, well, again, if you've got V over I, the units of the potential are volts, the units of current are amps, and so volts per amp is defined to be the ohm. And so ohms, just like for Ohm's law, same ohm, right? So we're going to write it as capital Omega. Ohms are the unit that we're going to use for resistance. What does the resistance depend on? Well, it depends on two things basically: the geometry of your resistor and the material that it is made out of. If we think about the simplest geometry possible, that's for a uniform cylindrical resistor. So basically you have a resistor that's built like a tube, and then the resistance of that resistor in that case is given by rho L over A. And so the rho here is the resistivity of the material. And again, we've talked about rho before. We said it's equal to 1 over the conductivity. The more easily your material conducts electrons, the higher its conductivity is, and therefore the lower its resistivity is. On the other hand, if you have a material that doesn't conduct electrons well, then that means its conductivity value is going to be low and its resistivity value will be high. So that's what rho is, resistivity. L is the length of the conductor, and A is its cross-sectional area. So again, since what we have here is a tube, we can basically define our cylinder via two parameters: how long is it and what's its cross-sectional area. In resisting current flowing across it, what that means is that your resistor dissipates energy. So energy is provided by the battery. That energy goes to driving a current, and then your resistor, in resisting that current flow, actually ends up dissipating that energy. So resistors dissipate the energy provided by a battery. How do they do that? Well, the electrons are going to drift in response to an applied electric field that's set up to drive the current. But effectively, those electrons don't move very far before they end up colliding with atoms. As they try to accelerate within the field, they basically bang into things. What your resistor is doing then is it's converting the kinetic energy of the electrons that's being converted into the thermal energy of the atom. So as the electrons try and accelerate up, then they bang into something, and so that attempt to sort of increase the kinetic energy of the electron effectively is lost through that collision. But where does it go? It goes into effectively increasing the thermal energy of the resistor due to those collisions. So how can we calculate how much energy is dissipated in a resistor? So we know that if we start with charge, and again, we're just going to use our standard designation that the current flowing through is really positive charges as they move. So here I've got a positive charge sitting over here at the high voltage end of my resistor. It will move from the high voltage to the low voltage end of my resistor. That takes some work. I can calculate out that work, a little differential element of that work, by thinking about some tiny charge dq as it's moved across that voltage difference. And so when I think about the power, the rate at which energy is dissipated, that's what the power is telling me. Well, the work that's done in moving that charge across my resistor, well, that work is basically how the potential energy is changing, and what I'm interested in is figuring out that rate per time. And so when I plug in the work done to move that charge, that's my dq times v, that's still over dt, and what I notice is I end up with dq over dt times v, and well, dq over dt, that is the current. The rate at which energy is dissipated within a resistor is given by the current flowing through the resistor times the voltage drop across the resistor. Well, of course, that's one way we can write it. Ohm's law gives us two other options. So if I eliminate I or V, then I have two other expressions that give me three ways total that I can calculate the power, depending on which of the three parameters I know. So if I know the current and the voltage, P equals IV, that's going to be the one that I want to use. If what I know is the current and the resistance, well, I can get rid of the voltage by plugging in V equals IR, and I'm left with a second way to calculate the power. The power is equal to I squared times R. Or if what I want to get rid of is the current, because what I know is the voltage across my resistor and its resistance value, then again I can solve Ohm's law for I, substitute that in, and I'm left with an expression for the power of V squared over R. So all three of these are equivalent. Basically, it's just which two of the three parameters do you know in terms of figuring out which one of these is the easiest one to use to make your power calculation.